Okay, hello. So I'm gonna make a very quick video right here, talking about a video made by someone called Logan Smith, right? So if we go to his channel, he's a YouTuber that makes plenty of, C++ versus Rust kind of videos and stuff like that, right? And he made a video called Rust Functions Are Weird, but Be Glad, right? So we have to be glad about it. And he made a whole part of video explaining how C++ is not capable of performing monomorphization the same way the Rust does, the different type system. How this example right here needs to use like a lambda to be able to work properly or whatever, some weird stuff. Like he says that, let me see if I find the comment right here. Talks about how, okay, so there was this person right here saying that he doesn't understand the complaint, right? Like the video is complaining about a problem in the C++ code, that the compiler doesn't know that what function calculate is going to be calling by receiving it from the function pointer right here, right? And that's the entire point of passing a function as a pointer, right? Logan replies saying that you are confusing static polymorphism with runtime polymorphism. The template provides a static polymorphism, blah blah blah. As far as he goes on to say that basically that the C++ compiler is forced to use to generate a lot of runtime code to dereference a pointer to make a function call, right? When you got all the information at compile time, and you should be capable of actually performing this code entirely compile time, right? But that it is not possible in C++ because of the type system. And I'm here to demonstrate that he's wrong, and the problem is that he does not understand the type system in C++. So let's first run through this. This is the code that he left in the description of his video, right? First of all, want to clear out this attribute no inline. A lot of people are saying, oh, but you're telling it to not inline the code. Don't misunderstand, people, right? I'm gonna talk about that first. This no inline is telling the compiler to not inline the call to calculate, right? Like if you go to main, we want to be main and see it right here. Hey, we're gonna be calling this function right here. Like this is what you want to call. This is what you want to see. That is what it's doing right here, so that you don't have directly 3 lines of assembly that return the value 20, right? No, what you want right here is to have a function call to this function calculate right here, and then get all of the code to calculate. That is the thing that we want to see right here, okay? That is the thing that we want to see right here. So, since that's the thing that we want to see right here, right? That's why we write this attribute no inline, so that we can actually see the function call. That is literally all it's doing. This has nothing to do with all of this thing right here. That's the first thing I wanted to clear up, because there are a lot of people who get confused about this and think that's the problem. No, it is not. So where's the problem? Well, we got an stdio stuff. We're going with a transform, basically reducing all of this, and we're adding up from 1 to 5, right? That's it. And what we're going to be doing is adding the results of this function that we pass as an argument to calculate, right? And it generates all of this code, which what it's doing is referencing this pointer that we're passing. We're passing a function pointer right here, right? And that is precisely the problem. The problem is that you're telling it to make a template that takes some kind of type name or class named quote-unquote T in this context, right? And then you're saying that you want to have a T named F, and we're going to use this F. So this T right here, when you pass F to this place right here, this is going to be a function pointer, and it is a pointer that looks something like this. It is a pointer to, under the hood, it could be like a pointer to int. Basically, this would be the name of F under the hood, right? And with the C++ notation, it would be int. Basically, this is the quote-unquote under the hood C notation of sorts, right? And that's it. right? Like what you're telling it is to pass a pointer to a function that returns int and takes one int as a parameter, because you know the function types in C++, they are not monomorphized for each function that you create, right? Like the type depends on the return value and arguments that you take inside. So that means that there's none of what the Rust thingy offers by default. It is you work with function pointers all the time. Since you work with function pointers all the time, you're basically telling it to do something at runtime, because the compiler cannot guarantee that this value right here that you're passing it is going to be always the same, because you don't know if you're changing this pointer somewhere else. You don't know where the operating system or the computer is going to be allocating this memory of this function in when you load the program, right? Like you could have the guarantee of an optimization when you know that you're working with an offset relative to some static pointer or something, right? Yeah, but that's not the case here. That's why you get this pointer passed into the arguments. It's literally telling it right here, you're taking an int pointer int, right? Like it is literally what I wrote. It's right there. It's taking that as an argument for the template and as the argument of the function. So basically you're passing it a pointer and you're going to dereference that to get the result of calling this function. That's it. So you got all of this runtime code right here, which sucks. How do we prevent that? Well, let's come here and let's write it from the ground up. Actually, I'm gonna first show it in GCC, which is my preferred compiler, and then we're going to actually write it in Clang to see that it does the same. So the way that I would do it, right, is obviously I'm gonna be using first a for loop because I find it more attractive. So we're gonna have an int main, we're gonna have our main function, right, and we're going to return calculate of fn, right? We're gonna make the static int fn int x return x plus x, the same thing he wrote, right? So that's it. Now we're gonna write the rest. We got the template. We're gonna take a type name. We're gonna call it f for the function, right? We got an int calculate ff. We're going to do int ans equals 0, return ans, and we can just iterate for all of them. For int I equals 0, I is smaller than 5 plus I. That is what he's doing. I think he goes from 1 to 5, right? So ans plus equals f of I. Basically, that's what he's doing. And this works. And as you can see, we get this result right here. Why? Because we didn't tell this to not inline. So what do we have to do? Well, we have to write the exact same thing right here. The attribute no inline. And also, well, this is a static. If we remove the static, it would work the same way. We're just gonna keep it. So why is this not working? We got attribute no inline int calculate. I am sorry, it does not go there. It goes here. So we now have our problem right here, right? And you go, how do we fix this, right? Well, as I said, we're passing a pointer right here. So all we have to do is tell it right here, hey, instead of taking some unknown type here, since we know that our function is going to take int and return int always, well, you can always change it. We can just say int. We're going to take an int pointer f int. We get rid of the arguments. And now this compiles properly. We're going to change this. And now, ta-da, we got our code running completely compile time. Why? Because we're actually, if we want compile time code generation, we have to use the compile time code generation mechanism. We don't use the runtime code generation mechanism, right? Like, not code generation, sorry. If you want compile time stuff, you use templates because they are compile time. You don't need any lambdas or anything like that. If you wanted it to be runtime, then you pass the function pointer. That's precisely the thing that we're doing right here. Okay? So yeah, that's it. That's basically it. We got the same code as he does. And this was what I wrote before, which actually made use of a macro right? To make things a little bit nicer, so we can just go ahead and say, define calculate of some function as calculate internal of this function. People might say this is ugly, but like it's a perfectly valid solution, right? So there we go, we got it. Same code generation. And if you don't believe this works, we go here into trunk with Clang, and we got the same. We got main, we jump to the calculate, and we move EX, return 20, and that's it. Exact same code generated by both situations, right? And this right here would be the fixed version of sorry, this isn't it. One over to the right. This will be the fixed version of his code making use of modern C++. It's exactly the same thing. It works with iota, transform, and reduce, right? It works perfectly fine. I had it here prepared to demonstrate that it's the exact same thing, and you can even use the macro if you want, and it'll work, right? Now, why does this happen? Well, if we go over to the Rust code right here that he posted himself, this works because right here we're telling calculate generic of f that we're going to be taking some variable named bar that is of type f. And since all of the functions are monomorphized, that is, they are their own type, they don't share any type. Like, this is not a function of i32 returns i32. No, this is of type whatever the type of f is and whatever the type of f prime is, right? Which means that each function exists himself have their own type, right? Sorry about that. This was a demonstration for a later part of what I wanted to talk about. So basically what is happening right here is the same thing like what we were doing in the other example, right? It's just taking this function as a parameter, but since it is monomorphized, it's not a function pointer. It is the function object itself, quote unquote, right? It's as if it were taking some kind of identifier that we know of at compile time, and that is why we can write it this way. So when you write this in C++ and when you write this in Rust, you're not writing the same thing. Here you're saying, hey, I'm going to take a function of this specific type, and there is only one function of this type in the whole code, so it must be that function, so the compiler knows it, because this is not a function pointer, this is monomorphized. It is kind of like a quote-unquote identifier for the compiler, right? But from the point of view of C++, what we have is a function pointer. And since it's a function pointer, we're going to get runtime polymorphism, which is what you wanted to avoid. And that's the reason why, if you want this to be compile time, you need to pass as the template argument the function quote-unquote pointer, so that the compiler knows, hey, this thing right here is a template argument. That means it is something that I know about at compile time. If you pass it right here, it is something that you could be passing something generated during runtime. You don't know if you're loading a DLL or whatever the fuck. But this right here is something that 100% that is going to be the way that it is when you're compiling this code. So that's why if you pass this as the template argument, it works. You can write the exact same code as Rust, and it will now work correctly, right? So now, moving on, let's go see this example right here where we actually are making use of a function pointer in Rust, so that you can see that we also generate this whole lot of runtime code, right? It's doing the exact same thing. If you look at what this generated, and you look at what this generated, basically, despite a few minor differences, it's the same thing. It's the referencing a pointer to a function, and it's calling it. So if you make use of a function pointer so that you can pass any function to it rather than having a specialized, because when you're making a template, you're making a quote-unquote special version of calculate tailored to that certain function, right? So if you make it use a function pointer, even though it is obvious to us that this is the only f that exists, the Rust compiler also does not know that it can perform this compile time optimization, because you're telling it use a pointer, And Rust goes, okay, but I don't know if this function pointer is going to be this value always, or it could change, or whatever. I don't know what it's gonna be. I have no guarantees that your code is only this thing right here that I'm seeing. So that's it. Runtime polymorphism that you complained about, right? That is why this code that you see right here is not exactly the same as C++. Like, you don't have a one-to-one notation. If you want to get the equivalent code, it's going to look completely different between C++ and Rust, right? That is why this thing right here works the way that it does, because you're basically doing the equivalent of passing the function itself as the template argument in the C++ code. Because C++ does not do that monomorphization thing with functions. Each function has a certain type, which depends on the return type and the input arguments. And Rust, the specific type of each function is itself. So that's it, right? That's the difference. Now, the other part that I wanted to talk about, which he says is a optimization that the compiler is capable of doing, which he doesn't demonstrate properly in the video. Actually, he demonstrates it like this, and that's not good enough, because a lot of people actually complain about this. Because if you have death code removal, like if you look at this, people could go and say, hey, this is actually just death code removal. You're removing f prime. You're not optimizing it, because he says that this monomorphization can be detected if both functions are determined to be equivalent by the compiler, right? They can be quote-unquote merged together into one single function, and then the calculate template instantiations are actually not generated as different, and it's the same one, right? And people will go, oh, but that's death code removal. No, it's not. He's actually correct about this thing, and I can prove it. As simple as calculate f prime. Like, we add up both results so that we don't have any death code removal. We return this, and since we're making a return value of both function calls, you can see that we still have one function and one calculate. Why? Because he is correct about that thing. Rust is capable of actually determining that both of these are the same thing, right? And we can go over to C++ and we can get the exact same result. So we go to this code right here that we wrote before, right? We can make another version, which is static fn2 returns x times 2, right? And we can say calculate fn2. And as you can see right here, we actually have our calculate internal of 2 instantiation types in here, right? And we call them both. But if we go over to GCC, GCC is actually capable of generating only one of them, right? Like, that depends on the compiler. Same way that GCC doesn't actually generate these functions right here, but Rust does. These are minor differences, but as you can see, this compiler right here is capable, perfectly capable of understanding that if we're returning this value, there is no death code removal. The reason I'm adding them up is an example, because I could just say calculate fn here, for example, right? And then do like this, and then we have calculate remove through death code removal. So because it's not actually used, it's completely it's a value that goes unused, so it would be optimized away. And the same happens in Rust. So that's why I'm returning the addition of both of them. So you can see that we actually get the exact same thing. So both Rust and C++ are capable of doing the exact same thing and generate the exact same assembly output, or very similar assembly output, with optimization enables. Because, you know, the problem that you were experiencing was that you actually misunderstood what the C++ code was doing, because you don't understand C++ type system. That's the problem, right? And to top it all off, one last thing I want to mention before I finish the video, because there's nothing else to be said. When you explain that thing about the need to make use of a lambda in C++ being a common solution or whatever, I've never seen that. I'm sorry. I mean, I guess maybe modern C++ people do that all the time, but I myself have never seen that thing. Like, the solution that I've always seen, and that is the oldest solution known to C++ programmers, is just making a template specialization or instantiation, like passing it as a template argument. The thing that I demonstrated right here, right? Like, that is literally the solution that I've always seen. I don't know, like everyone I know who programs in C++ for a long time would go this route. There is no need to make use of a lambda or anything like that. So yeah, there's really nothing else for me to say. It's just that I wanted to clear things up because, that video kind of like says things that are correct but also has misinformation, and I don't like that. So yeah, that's it.